Today you are going to learn about the binomial theorem. Okay, let's start with something pretty simple. Okay, if I ask you to expand the following, in this case x plus 2 and everything squared, what are you going to do? Well, this might remind you about the formula that you learned back in Algebra 1, where you know that it was x squared plus 2 times 2x plus basically 2 squared, which is equal to x squared plus 4x plus 4, okay? Or you can use it via the using foiling. That would be okay too. Whatever it's your method, that's fine. Okay, now if you need to do this, what would you do? If you need to expand it, okay, I would think about this and then multiply it times another x plus 2, and then you would have x power 3 plus 3 times 2x square plus 3 times 2 square x, and then plus 2 to the power of 3. This is the same as x cubed plus 6x squared plus 12x plus 8. Okay, and that's the expansion. However you are doing it, that's fine. Okay, via foiling, it doesn't matter. Now, if I ask you the same question, but now to the power of 4, what are you going to do? Now you're going to use this one, and you are going to multiply times x plus 2, okay? Or as I see it, okay, I'm using the Pascal triangle that we're going to see. That's why you are seeing like, that looks weird, okay? So x power of 4, I know that the next one is going to be 4 times 2x power 3, okay, plus, and then I know that it's going to be 6 times 2 square x squared, okay, plus 4 times 2 cubed x plus 2 power 4. Okay, you're going to tell me how in the world you know these numbers. We are going there, okay, because I'm pretty sure you're going to be doing it via foiling at this point. Okay, but after this video, I'm pretty sure you're going to use the Pascal triangle because it's pretty simple. Okay, so when I simplify all that situation, okay, you have this. Okay, are we okay with that? So hopefully you get where I'm coming from. Okay, so as you can see here, you saw that it didn't take me a lot of time. I didn't foil it as much, okay, to expand my binomials, okay? Why? I'm doing what we call the binomial expansion, or the Pascal triangle, which we are going to see, okay? So we call it the binomial theorem, okay? And we are going to define a new terminology that you are going to find it super simple. It looks a little bit weird, okay? So my notation, it looks like this, like a big parenthesis, and you have a number here and another one here. Okay, please note that the number on the top needs to be greater or equal than the one at the bottom. Okay, so if we have j and n are integer numbers with 0 less or equal than j and j less or equal than n, you have this symbol, okay, parenthesis n and j. And we define it as the following, okay? So you have that it's going to be n factorial divided by j factorial times, and please use a parenthesis here, n minus j factorial, okay? So I have 3 factorials here, okay? I know that it looks a little bit intimidating, but with the following examples, you're going to see that it's not that bad, okay? So using this formula, okay, so this one, important. I would put a star here because it's quite important. Okay, so if you need to, we call it the combination notation. Okay, so find the values of the following. You should use a calculator to evaluate D. Why? Because it's huge. Okay, for the others, we don't need anything. Okay, so 4, and you're going to have your calculator all the time so you can use it, but for this, I don't even use it. Okay, so you agree that n is 4 and j is 1. Okay, so you have 4 factorial divided by 1 factorial times 4 minus 1 factorial, which means that this is going to be equal to 4 factorial divided by 1 factorial times 3 factorial. Okay, Please note that I have this parenthesis here because otherwise you would do only the factorial for 1. If you don't put the parenthesis, the calculator will do something crazy. Okay, so here the cool thing is, you know that the factorial of 4, what's the factorial of 4? 4 times 3 times 2 times 1. Okay, so that's 4 factorial. And you know that this guy is 1. And this one is going to be 3 times 2 times 1. So the cool thing is, this cancels, and what's 4 over 1? You know that this is 4. And that's it. Okay, so that's the answer for this part. Okay, now let's look at this one. What are you going to do? Same. Okay, so you have apply the formula. You know that it's going to be 6 factorial divided by 2 factorial times 6 minus 2 factorial. You know that that's going to be a 4 factorial at the bottom. Okay, so you have the situation. Okay, you know that from 4 to 1, basically they are going to cancel. So what do you have left? I have left the 6, the 5, of course the 2, and the 4. Okay, and actually I don't have the 4. I already canceled it. Okay, so you have this. Okay, but you can simplify it a little bit more. This 6 and this 2, you know that that's a 3, so 3 times 5, it's 15, and that's it. Okay, so as you can see, pretty simple. Okay, now let's move on to this one. What are you going to do? Well, you have that it's going to be 10 factorial divided by 9 factorial times, and it's going to be 10 minus 9, that you know that it's going to be a 1 factorial, so that's a 1. Okay, so you realize that the 10 factorial is bigger. Well, let me write it like this so you can see what's going on. Okay, so this one is a 1, so it's there. Okay, you know that this factorial is bigger than this one, having 10 divided by 1, which you know that it's 10, and that's it. Okay, so as you can see, in this notation, you're going to cancel out most of the denominators. That's the reality. Okay, and you're going to simplify. Okay, so the key here is simplify. Okay, now this one is big. What's going to happen here? Well, you use the formula exactly the same. Okay, don't let the notation to intimidate you at all. So you have 50 minus 10, okay, factorial. Therefore, so you have 50 factorial divided by 10 factorial times 40 factorial. Okay, so you're going to tell me, okay, so here I have, I can cancel a bunch, but I still have a lot. True. Okay, so you can cancel basically everything up to 40. Okay, but then you have all the 10 factorial and then 50 through 41. Okay, basically. So let me just grade it here so you know what's going on. Okay, so you have 48, 42, 41 at the top. And then at the bottom, what are you going to have? 10, 9, 8, 7, 6, 2, 1. Okay? So that's what you have. Okay, so that's why we need to plug it in the calculator. Let me put it here. Okay, so when I plug all of this in the calculator, that it's going to take me some quite time. Okay, I'm going to have a humongous number that, let me give you the number, is 10, 2, 7, 2, 2, 7, 8, 1, 7. As you can see, huge. Why it's huge? Because the multiplications of this are humongous. Okay, so that's why. Even though you can simplify, well, it's still huge. Okay, so let's move on to the next page. Okay, so on the next page we have more notation. Okay, more than notation is like FYIs. Okay, so useful formulas involving the combination formula. Okay, so you know that the combinations from n to 10, what are going to be these ones? Okay, all the time when you see the 0 here, no matter the number that you have here, it's going to be 1. Okay, remember, the n needs to be positive, so you know that that's 1. Okay, so this one that you have over here, it's pretty nice. Okay, so you have n and 1. This is always going to be n. Okay, now the cool thing is, let's say that if you have a 9 and an 8 here or something like that, okay, it's going to be always n. Okay, now if the two numbers are the same, which it can happen, it's weird, but it can happen, you have that this is a 1. Okay, so remember, n is going to be an integer, a positive integer, so that's what we have. Okay, so let me introduce you to the Pascal Triangle. Why we call it the Pascal Triangle? Well, we are going to use a bunch of combinations. Okay, 0, 0, 1, 0, 1, 1, 2, 0, 2, 1, 2, 2. Okay, and then 3, 0, 3, 1, 3, 2, 3, 3, 4, 0, for 1, for 2, for 3, for 4, and so forth. Okay, and you can go, this keeps going, as you can imagine. It never ends. Okay, so what do you notice here? What I notice is I start with 0, of course. Okay, this is 0, 0. Then all of this diagonal, basically, the j's are zeros, okay, and the n's start at 0, 0, 1, 2, 3, 4, 5. Then on this diagonal, as you can see, is 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, and so forth. Okay, so as you can see, every not column, every row, okay, the n is going to be the same. So here is my n is going to be 0, then my n is 1, and so forth. My n is 2, okay, and the j is growing, okay, from 0 to 2 or whatever, okay, or the n that you have in that situation. Okay, so that's what we have. Okay, so why we care about the Pascal triangle, let me show you. Okay, and why this is related with polynomials. Okay, so if we need to fill the values of each combination to create a new triangle, what are you going to do? You know that this value, 0, 0, is 1. Okay, why 1? Because you know that you have the situation or the situation, whatever you want to see. Okay, so that's a 1. Then 1, 0 is going to be another 1. Okay, 1, 1 is going to be 1. Okay, because you know that you have a situation like this. So with this, I can start the Pascal triangle. Okay, as easy as that. Remember, the outside lines are going to be 1s. Okay, so my Pascal triangle here, since I'm going to add this 2, this is going to be 2. Okay, here it's going to be a 1, and here it's going to be a 1. Okay, which is related because you know that the combinations from 2 to 0 is 1, and 2 to 1 is 2, 2 to 2 is 1. Okay, so let's keep building the Pascal triangle. Okay, following the same idea, what do you have? You have that this is 3 if you add them. If you add 2 and 1, is going to be 3. Now outside you have 1, 1. Okay, so this is basically the 4th level. Okay, so the next level that we have, you're going to tell me, interesting, yes it is. This is going to be 4, this is going to be 6, this is going to be 4, 1, 1. Are we okay with that? So this is basically the idea of the Pascal triangle. Okay, so in this new triangle with only numbers, we call it the Pascal triangle. It's named after the famous French mathematician Blaise Pascal, that he lived during this time. He passed away pretty young. What patterns do you notice in this triangle? Well, the Pascal triangle has 1s down the sides to get any other entry at the 2 nearest entries in the row above it, meaning if you want to find this one, you're going to add this 2. Okay, so we need to use the patterns you found in 2 to find the 6th row of the Pascal triangle. Okay, so we have how many so far? 1, 2, 3, 4, 5. Okay, so the 6th row, what do you have for the 6th row? I'm going to think that I'm here. Okay, so for the 6th row, the first one is going to be 1. This one that I have, the second one is going to be 5. The third one is going to be 10, okay, because there's 2. Then the next one is going to be 10 as well. And the next one is going to be 5. And then the last one is going to be 1. Okay, so this is going to be the 6th row of the Pascal triangle. If what you're telling me is that the one when n is equal to 6, what would you do? Okay, the following one. Well, you would do add this 2, add this 2, add this 2, also this 2, this 2, and you know that the outsides are always 1s. Okay, so that would be your 6th row. Good? Okay.